Hi, I'm Nadav. I'm going to talk to you today about time, about event time stream processing with Akka Streams. So that's me, Scala tech lead at Riskified. I've been using Scala since 2007 and Akka Streams for the last couple of years. So what we're going to talk about is, first of all, we'll talk about the concept of time windowing in streaming libraries. We're going to compare how much of that is available in streaming libraries as opposed to streaming platforms such as Flink and Spark. And then we're going to go over a library that we prepared to handle exactly that sort of thing with streaming libraries. So first off, I'd like to start with a question. How many of you use Akka Streams or familiar with it? That's a good number. All right. So how many use Spark or Flink? Any of you use both? Not that many. Any of you were faced with the dilemma of choosing one or the other? Not that many. But that's the dilemma that we were facing at the time. So we at Riskified, we do fraud prevention. In order to do that, we analyze behavioral user data as they browse the merchant's website. So part of the information that we gather is whether the user is behind a proxy or not. We try to detect that. That's one good indication of whether the user is trustworthy or not. So if the user is not behind a proxy, then on the client side, we are able to see that some latencies are fairly similar from the user's browser to the server and back. So in that case, that's probably a legitimate buyer. It's a good indication. On the other hand, if we see that there is some discrepancy, that might be an indication that this is not a legitimate deal. So we want to gather the lowest latencies for each session over 10-second windows. This is a motivating example. So let's run this through. First, we have the user's browser from which we measure and send latencies to our server. Then that arrives at the journal. This could be Kafka or Kinesis if you're on Amazon. And then we consume that information into a stream processing microservice where we assemble that information into 10-second windows from which we choose the lowest latency entries for each user. Only those we want to retain for later analysis. So that's time windowing, basically. This is a major part of what we're going to talk about here. So time windowing is available on both Spark and Flink and libraries such as Akka Stream on the other hand, except very limited form when it comes to streaming libraries. And we were faced, this is something that's important to us for the use case I described. So we were faced with the dilemma of choosing a platform, we were considering Flink, or Akka Streams as a library. So platforms are powerful, they're featureful, but if you don't have a Spark cluster available on hand and that's something that you haven't yet adopted in the organization, then it's a pretty big fish to catch. And also, there are limitations. To this day, Spark and Flink require you to use Scala 211. That's, I understand, a problem in the process of being solved, but even to this day. So basically, we found ourselves spot in the middle, just beyond the area of convenience where you can choose a streaming library and say, we're fine with that, but really, not really certain we want to justify the upfront cost of adopting a streaming platform for that use case. So instead of biting the bullet and going with full-fledged platform, we wanted to just move over what's possible, expand the realm of what's easy and possible for us to do on Akka Streams, especially as it relates to streaming libraries. To time windowing. So let's see how a simple implementation of, before we see the solution, let's see how a simple implementation deals on Akka Streams with windowing, time windowing. So the problem we saw earlier, we want to gather the lowest latencies for each user into 10-second windows. So we have our basic latency entry, that's a pair of session ID and the latency duration, and we want to take those. Now I'm not going to go through Akka Streams syntax in detail, but I see many of you are familiar with it. Those that aren't, it's fairly easy to follow. So we have our latency source from which those latency measurements are emitted. We partition them according to session ID. We then accumulate them into 10-second time windows. And once every one of these elapses, we want to find the lowest latency within that window. Once we have that, those substreams that we have, we want to merge them together and relay that downstream to arrive into the database. So, as I mentioned, this is naive. This doesn't achieve what we want. Not really. Because suppose we want to bring up first just the part that produces information. We receive latency reports from the client. We have our front end relay that information to the journal, and we accumulate events, and accumulate events, and accumulate events. And only then we bring up stream processing. So once stream processing kicks in, we have quite a backlog to handle. So instead of this nice measured windows reflecting actual data that we encountered, we get, well, I assume most of you arrived here by train. This is what happens when a train delays. So we get this. So the first few windows are going to be overloaded, our data is going to be skewed, and heaven forbid we encounter a bug, it's going to be very difficult to reproduce. The windowing is not going to be consistent because we are looking at the hardware clock. That's not something we want to do. Not in this case. In order well, our alternatives to processing time, the obvious alternative is to look at event time. The time at which the event actually occurred, modeled as part of the data of the event. The notion of event time is simply not available in any of the streaming libraries available in Scala today. We only have processing time there. So how do we get from having processing time related combinators in the streaming library to event time? Well, for that purpose, we implemented Glacier, or בעברית זגג, basically a name having to do with nice, pretty windows. Well, that's an event time windowing library that's supposed to fit into the gap where event time windowing is not available in streaming libraries. It was mostly aimed at Akka Streams originally, but since we are now working on adding mnemonic support for it. So now we're going to go through a tour of the API. Then we're going to peek under the hood at the implementation and see how it's tailored to use with Akka Streams. So, well, we start by basically augmenting our previous latency entry. Now we still have our session ID, we have the same latency timing data we measured, but we also have a timestamp, right? We're using event time. This is part of the data now. So let's go through a stream example of how Glacier is used. Here this is an Akka Streams based example, leveraging a few implicit conversions in order to enrich the API. The first three methods are provided by the library, the rest is plain Akka Streams. So first thing off, we're going to indicate how we obtain our logical timestamp. It's in the data. We're just going to drill into the timestamp field in the latency entry. Next off, we have our session ID. So this is what we want to partition by. And third off, and this is where it gets slightly more interesting, is we apply the windowing logic. So right now, as you see in the example image, we want to have 10-second windows adjacent to each other, non-overlapping. That's the simplest kind of windowing logic one can use. We'll see other options in a moment. Now, further down that same call, well, when you receive events with timestamp as part of the data, well, events aren't guaranteed to arrive in a monotonic order. Time can advance, but occasionally you'll also get an event that's staggered behind, that's a bit older than the others. In that case, we, as platforms support, we also make allowance for them. If an event is a bit late behind, we're going to keep the window around for just a bit longer, and it will still accommodate the late arriving events. So, to a degree, beyond that point, the event is going to be marked as a late event and discarded, forwarded to separate handling. So, after that, we're basically back in Akka Streams, plain API. We're in a substream here. So, what we want to do here is just pick the latest timestamp arriving, the latest latency measurement arriving, compare the latency to what we have so far, and this is our reduce over here. So, since many of you are familiar with Akka Streams, reduce won't emit a value for each value entered. There is nothing in it that indicates when it would terminate. However, once the window closes, the substream would terminate, and the event will be relayed downstream. So once we're done with that, we're just, as before, going to merge the substream, and that's what's going to be relayed onwards. So what other kind of, or actually, how do we represent windowing? Well, we've spoke already about tumbling windows. Those are non-overlapping spans. So a window function is a function from a timestamp to a sequence of intervals. In this case, we're going to get a timestamp and return just a single interval which the timestamp fits in. So the implementation for that is trivial, and there's no reason that we should go into it. But why do we actually need the list? Well, the next option that we have is sliding windowing. So sliding windows are just having a span of a set duration, and we then introduce a second span and another after it by a certain offset. So these are overlapping, and those are useful for running averages, for example. So we're not going to go into the implementation for that. These are basically this is basically how the API is exposed to the user. So internally, under the hood, this is based on immutable state. So each time an event arrives, we're going to look at some state that we have so far, that event, and then we're going to emit a modified state and a set of instructions for processing by the integration with the streaming library. The state that we maintain is the logical clock, the present time timestamp. So whenever a new event arrives, we're going to advance that if it is newer than what we already have. Otherwise, the time remains still. And we also, hold on. Step back. Oh. There we go. We also keep track of what windows are active at this moment. So basically we have this interval as a key, and any partitioning keys, for example, session IDs that were active during each interval will be in the set of keys for that interval. So that's the state. Now, if you look below, there's this representation that we're going to keep track of now as we process an event. So we start with having a timestamp at 19 seconds. And we already have the first interval of 0 seconds to 10 seconds with open windows, sessions that were active. And even the interval afterwards is also occupied with active windows. So this is basically the logic that we follow through in order to handle each event. So now an event arrives. So we have a latency entry with a partition key, a session ID of 4. The latency that was measured is 100 millis, and the timestamp, we are 22 seconds into the run, or 22 seconds is the time at which the measurement was taken. So the timestamp advances to 22 seconds. Also, we want to close the windows, close the old windows. Since now the timestamp is 22 seconds and our latency, maximum allowed latency is set at 1 second, then windows at intervals 0 to 10 seconds may close. So we're rid of them. And then we want to open some windows because, well, one window, because we now have a new event. And that event is related to session ID that hasn't yet been encountered in the 20 to 30 second interval. So we see below now a 20 to 30 second interval with a new partition, a new session ID. So now, well, so far we haven't really done anything. We've basically done bookkeeping. We've updated the timestamp, we've closed some windows, we've opened some windows, but no stream processing actually occurred. There was no logic. What we have been doing, though, is generating instructions to be followed right after step function. So we also generate one in order to handle the actual event. And we gather all those close, open, and handle instructions. Those would basically, for this run, look like so. Here we have a window status change where we want to close the window, the first two windows that we closed before. And afterwards, we also want to open a window, and then there's the event that arrived with the latency entry to be processed. How is that actually handled with Akka Streams? So up until now, we've been seeing this DSL, where we did some extension methods over Akka Stream API. This is what it actually calls. Here we have, the DSL basically assembles a glacier object that does the step function you saw earlier, and the flow that we want to do the windowing over. So how do we go about processing this with Akka Streams? So we use scan. We start with some empty windowing state. And now we have our empty windowing state, and the first event that came in, we run that through Glacier, and we receive a new modified state with some windows closed, some windows open, and some instructions for further processing. So we want those instructions to be spread out into a stream, and though each such instruction has a window object. A window includes partitioning interval. So for each window, and those can be multiple intervals, even for a specific key, for each one of these, we then partition them into a separate substream. Each such substream will be specific to that window, and we will let it run and process events until the point where we receive a close instruction, an instruction to have the window closed. But until that point, we're going to keep an eye out for handle event instructions and just relay that event onwards. So back in user code, we have our reduce, as seen in the previous example, where we want to keep track of the lowest latency measurement as events come in. And that is going to close the second that the window substream closes. So once we've done that, we merge everything back together. And we end up with the sample code that you see above. Now, this is functionally very similar to what you can do with the Flink API. As seen below. Now, I admit this is somewhat a bit of a pseudocode example, but fairly representative of how that would look. So this way, time windowing, as we had available to us before we got started, was lackluster on Akka Streams. We were only able to look at the hardware clock, and this didn't fit our need of treating timing data as part of our data. With Glacier, that's something that we can do, and the API is, well, state of the industry. So that's basically the library, and it is in the process of being open sourced, but it is already used in production and processes millions of events daily. Any questions?
So how does this work with Akka clustering, if at all?
Well, it does not relate to Akka clustering at all. It's entirely separate. What we do is, well, we currently use it actually with Kinesis on Amazon. So we have our integration consumer library, which allows us to, well, it's very similar to how Kafka consumer would also work, Kafka consumer group. So we basically treat a consumer group as a stream. Each such one is a stream. We provide it a sink. So we basically build a sink using Glacier and that up to the source stemming from the consumer group. In summary, libraries are versatile and flexible. Platforms are, well, kind of have their strings attached. You don't always want to adopt one for a microservice, for example. They're powerful, they require some upfront investment, but they're also constraining. On the other hand, libraries flexible, but have their limitations. And, well, if you want to address those limitations by borrowing from what you have available on platforms or looking elsewhere, there actually can be a significant overlap of what you can accomplish with libraries that you use in day-to-day programming. Well, thank you.